Hi, my name is Inderjit Dhillon, and I welcome you to my keynote talk. When I first got the invitation to come to Singapore, I was super excited. I really wanted to visit Singapore, but oh well, I guess that will have to wait for another day. I do miss the fact that I would have had a live audience, eager and excited audience members. So I've tried in a very small way to replicate that over here. So here's my very enthusiastic audience that also doubles as my family, and they seem very eager and enthusiastic right now. Okay, that's great. So let me share my screen. So the topic of my talk today is multi-output prediction, theory and practice. When I teach machine learning to entering students, we always talk about the case where there is exactly one response variable or one output variable, both in regression and classification. But nowadays, there are many problems in modern applications that really are multiple output with possibly millions to billions of outputs. But let's start slowly. So this is the outline of my talk. I'll talk about the challenges that come in these multiple output problems that come from modern applications, missing values, the outputs themselves having features, sometimes the unavailability of negative examples, and then the problem of really scaling it up to very, very large output sets. So traditionally we have single output problems, for example, spam detection, handwritten digit recognition, or regression where there is exactly one target variable or one output variable. So here is the setting over here. We have a real valued response Y. The training data is Xi, which can be assembled in a training matrix X. So traditionally, we want to get coefficients W so that we have a linear predictor where XW is nearly equal to Y. For the regression problem, the squared loss is what we want to use, and that leads to the classical least squares regression problem. And it has a closed form solution. In the case of classification, we have two classes. It can be captured by just one response variable where Y is +1 if the training data belongs to the first class, and 0 or -1 if it belongs to the second class. And what linear methods do is find a linear decision boundary between the two classes. And so you can think of it as empirical risk minimization, where you have a loss function. The loss function can be least squares in case of regression, or in case of classification, it can be either logistic loss or hinge loss. And then of course we have a regularization term. And if you really look at textbooks, you can see that, for example, this is the textbook by the Stanford statisticians, Hastie, Tibshirani, and Friedman. Chapter 3, linear methods for regression. Chapter 4, linear methods for classification. And then there is a very small section in this chapter. I think it's actually only a couple of pages about multiple outputs. You look at a different textbook, same two chapters, linear methods for regression, linear methods for classification, and just once again, a very small section on multiple outputs. But that is the subject of my talk today. So multiple output prediction, it comes up in many modern applications. So for example, this is the Wikipedia tag recommendation problem that we'll carry out as a running example throughout my talk. So this, as an example, is a Wikipedia page on machine learning. And down below, hopefully you can see my cursor, are categories which are associated with this particular web page, or this Wikipedia page rather. So you can see the tags over here. You may not be able to read it, so I've written them over here: learning in computer vision, machine learning itself, learning, and cybernetics. So if we now treat each of these tags as an output, then the number of outputs can really be very large, millions, tens of millions, even larger. In the ad recommendation problem, if you're an advertiser, then you want to select the phrases for uh, um, having AdWords. And so, for example, the problem over here is given, let's say, a web page, can you automatically try and figure out the bit phrases? And each bit phrase would then count as a possible output. Similarly, tags with images. So modern multi-output prediction problems have lots of challenges: correlated outputs, missing output values. So let's first tackle that first challenge and see how we can handle these correlations in the outputs as well as missing output values. We use the same framework. Now my target variable or output variable, instead of a single vector, is now a matrix itself with m columns. But if I think of it as a regression problem, I can actually treat it very similarly as before. I can think of just independent coefficient vectors wj for output vector yj, and I can go through the same machinery, get a least squares objective, and in this case, I have a closed form solution. In the case of multi-label classification, I can get independent binary classifiers for each label, and that's sometimes called binary relevance. And this has been, but this method does not exploit any relation or correlation between the output variables. But when there is correlation between the output variables, we can handle it, for example, by putting a low rank model for the coefficient matrix. And this has been done long ago. So this is a paper in 1974, which did reduced rank regression. And in this case also, it turns out that even though you have a low rank constraint, which is a non-convex constraint, the wonders of the SVD, or the singular value decomposition of the coefficient matrix, allows us to actually get a closed form solution for this problem. So everything is, pretty easy so far. Now, if you really carefully looked at the example that I showed you before, we have this Wikipedia page on machine learning, and these tags or categories, these tags are, kind of quite incomplete. For example, you would think that there would be a tag called data mining, or there would be a tag called pattern recognition, and those could be associated with this particular Wikipedia page. So what ends up happening in real applications is that even though you have many, many, many different outputs, there are lots of missing values. So now this is the situation that we are in, that we have m output variables, but there are many missing values. And in applications, more than 99% of the values could be missing. So we can actually take the same approach as we did when there were no missing values. And to exploit the correlations, we can put this low rank prior on the coefficient matrix W. And if we do this, the problem in this case is that there is no closed form solution. So you get a similar objective as before, except now you only have this objective or the squared loss only over the known values, and you kind of ignore the missing values. And at the same time, you have a low rank constraint on the coefficient matrix. Now, if you look at this problem long enough, it actually reminds you, or it should remind you, of the matrix factorization or the matrix completion problem, except that now we have features associated with the inputs for which we are trying to make the prediction. So borrowing from that matrix completion idea, we can think of relaxing this non-convex constraint on the rank of W, and get a convex relaxation, which is that the nuclear norm is less than equal to a certain value. That's algorithm 1 over here. And then in algorithm 2, what you can do is you can explicitly factor W in terms of W1 and W2, each of which is rank K, and then solve this by alternating the solving for W1, solving for W2. This is not a convex problem, so it is a problem non-convex optimization. But once you fix W1, the problem for W2 is convex and vice versa. So algorithm 1 is a convex relaxation. Algorithm 2 is actually non-convex optimization. And both these methods actually work quite well in practice also. Now, in many applications, what ends up happening is that outputs also have features. Now, if you think about this, when you have the single response variable, let's say in classification, then typically there is really no need for having features with the class, right? But over here, you actually can have features with the class. And we can solve this problem by using an inductive version of matrix completion. So let me show you what I mean in this case, that not only do the training examples have features, but the outputs, which are represented by the jth column of the target matrix Y, they also have features. The outputs also have features. For example, in the Wikipedia example, there is a phrase, and that phrase itself can be thought of as features. And then there are other examples where the classes may, or the outputs may have features. Now, what you need to do over here is you need to try and model these dyadic or pairwise interactions between, let's say, the feature vector for the training example xi and the feature vector for the output variable zj. So one of the simplest ways to do it is to move from linear models to bilinear models. So the prediction then becomes X, W, Z transpose. X and Z are the features of the inputs and the outputs respectively. And then W is the coefficient matrix. And I can again solve this problem in closed form. If I put a rank constraint to try and exploit the correlations between the coefficient matrix, then still, again, because of the wonders of the SVD, you get a closed form solution. But now, as I told you before, in real life, most of the applications actually come with missing values, as a result of which there is no closed form solution. And then you need to come and use the same kind of algorithms that I mentioned to you before. So these are two algorithms for the inductive matrix completion problem, where in the first, as before, we relax the rank constraint in a convex way, get a nuclear norm constraint, and we get a convex relaxation. You can solve this problem for its global optimal. And then in the second case, you do alternating least squares. And again, these methods work well in practice. And then one of the questions is, well, what can you actually say about the theory behind these methods? So since I told you that these methods were motivated by the matrix completion literature, let's review that literature a little bit. So in the matrix completion literature, there's only a target or output matrix. There are no features along with the inputs or with the outputs. And the matrix completion or the matrix factorization problem in recommender systems is that given this matrix Y with lots of missing values, can we factor it with W1 into a product W1, W2 transpose? And then what can you say about this? How many values do you need to be able to recover the ground truth? So in some beautiful theory, Candace and Tao, and then Candace and Recht showed that you only need to observe, this order tilde k and entries where we've kind of ignored polylog terms in k and n. But by just observing basically order k elements per row, then you are still able to recover this matrix completely. Note that the full matrix would have order n square entries. So what about in the case of inductive matrix completion? Okay, so the question is that the matrix itself might be very, very, very large, right? So you may have observations on hundreds of millions of users. You may have observations on, million, let's say, movies. And the question is, can you recover this when you are given features with features with the input or the users and the outputs or the items or the movies? And what can happen is that maybe the number of features can be actually much smaller than the total number of users. And then the question becomes, do I actually need to know samples which are linear in n, or we can actually do by with many fewer samples? Note that the degrees of freedom in this coefficient matrix are not n times k, but it's actually d times k, where d is the dimensionality of the feature representation. So it turns out that yes, you can show these results. So along with my students and my ex-student, well, two of my ex-students now, we showed this result in a 2015 paper that said that yes, you can actually get recovery guarantees for inductive matrix completion for both the algorithms, for the algorithm that minimizes the nuclear norm and also the algorithm that uses alternating least squares. And this method is actually used quite a lot in practice. So let me just go back and make a couple of analogies first. If you look at matrix completion, you see on this slide that on the right-hand side, I've drawn actually a neural network which corresponds to the matrix completion problem, okay? So let's look at this neural network. So here we don't have any features. So we are essentially taking the features to be the identity matrix, or you can think of the feature for the ith input as the one hot encoded vector with just one in the ith place. And similarly for the outputs. And then the W1 can actually be viewed as an embedding of the inputs. W2 can be viewed as an embedding of the outputs. And the prediction is then given by an inner product between the corresponding rows of W1 and the corresponding column of W2 transpose. Once we have inductive matrix completion, we are actually given, let's say, features for the inputs, which are denoted by the X's, and features for the outputs denoted by the Z's. And so you can think of this as a two-layer neural network, where in the first step, you get an embedding of the input features. Similarly, you get an embedding of the output features, and then you can do the inner product to get the prediction for the ith input and the jth output. So there is a neural network connection. Of course, this is a linear or a bilinear method, and so there are no nonlinear activations over here. However, this is actually used quite a bit in practice, and that's what this slide shows. So this is a deep structured semantic model, which has been used for web search. This paper came out of Microsoft research. And this is an example where now you don't have a simple one-layer neural network, but you have actually multiple layers. In this case, I guess there are about 5 or 6 layers, and there are non-linearities at each step. So inductive matrix completion is used in practice quite a bit. Over here, what I showed is that the bilinear inductive matrix completion method actually comes with theoretical guarantees. And one question might be, well, what about these deep learning models? Well, we are not all the way there yet, but we were able to last year show and prove that neural network models for inductive matrix completion, you can actually give theoretical guarantees. So non-linear inductive matrix completion, you can give theoretical guarantees. Of course, there are some assumptions in this work. And right now it's only for one hidden layer, but with non-linearity, such as tan H and redo. And the next steps are, can we actually give results when we have deeper networks? So I've shown you solutions for missing output values and outputs having features. One other common problem in many modern multiple output problems is the fact that these can be viewed as positive unlabeled learning, right? So what does PU learning or positive unlabeled learning mean? Let me motivate it by a particular example that I worked on with a biologist colleague of mine. So my biologist colleague had a data set where he has worked for several years, actually maybe even a decade, on trying to get gene networks which have functional relationships between them. So for example, in this gene network, there's a gene AVP and AVPR2, and there is an edge between these two genes. And this is because a functional relationship has been discovered between these two genes. So my colleague, Edward Marcotte, has worked on these problems for quite a bit. But then he also, along with it, has data sets that that actually have known linkages between human diseases and these genes. Okay. Similarly, phenotypes in plants, diseases in rats, these dotted lines are known relationships between genes and diseases. And then, we can try and design a method. So we've actually tried to apply inductive matrix completion over here, because the genes have features and the diseases have features. So then we went back to the biologists and said, hey, can you actually tell us what diseases are not linked, or what genes are not linked with this particular disease? And they were very reluctant to actually give us an answer. And they said, they cannot really rule out any gene from being linked to a particular disease. So that means in this example, we only have positive examples, but we actually don't have any negative examples. And so that is the sort of problem called PU learning. So we have, traditionally we have supervised learning, semi-supervised learning, and unsupervised learning. But now we also have PU learning where we have just positives and unlabeled. Okay? So what that means is that there are no observations of the negative class that are available. And so we can now go back to bilinear prediction, or this inductive matrix completion idea. And the inputs are features, the outputs are features. We have this coefficient matrix W, we have missing values, but the additional complication is that we only know ones in this matrix, that is the positive instances. Many applications, we believe that most of the elements over here are actually negative examples. And so there are very few more ones that are to be discovered, but we actually do not know which ones are the true negatives. So one thing that people have done, people have observed this problem empirically and said that instead of solving this inductive matrix completion problem only over the known values omega, that we should actually take all the values into account, give a high weight to the known values and a much smaller weight to all the other values, with this belief that these are strong positives and these are weak negatives, but you are basically saying that everything else is a weak negative, right? So there was a paper written on this, which used this method and saw that this kind of biased matrix completion approach gave good results. And it turns out that one can actually build a theoretical, a statistical model and actually show theoretical guarantees for that particular model. So for inductive matrix completion and for matrix completion also, we have a paper that actually can give theoretical guarantees that we can actually recover the ground truth from, again, sampling from fewer features. And in practice, we can apply that idea to the problem that I mentioned to you before about predicting diseases, gene-disease relationships. So given, let's say, a particular disease, can you try and predict genes that are related to that disease? And here, now you can try and put lots and lots of data as features over here. So for example, gene networks, these data from different species, when we map them on all onto the human genes, we can look at microarray data, do PCA, and we can basically bundle them all together and put them as gene features. Similarly, we have disease features. We can look at literature, let's say from PubMed. We can look at comorbidities of diseases, and so we can form these features. And then we can do this PU, inductive matrix completion idea, and we published that work in bioinformatics. So so these are substantial challenges, but one of the big challenges that I haven't really gotten to is scaling up. Now, matrix completion and inductive matrix completion does scale up to large problems. One of the issues with these methods is that when you are trying to do inference, or when you're trying to find out, what output is relevant to a given input, then that inference time is linear in the number of outputs. So for example, if you have users and movies, this kind of says that you need to, for a new user or even an existing user, you need to kind of go through all the movies, even though you are only interested in the top K predictions. So the question is, can you somehow quickly prune out this output space so that you do not need to search over all the output space? So then now let me talk about some recent work which we have done, which enables us to do so. So this is what we call prediction for enormous and correlated output spaces, or PECOS. So this problem is sometimes called extreme multilabel ranking. And so just again, to set the stage, we have a training example. Right now, we'll just ignore output features just to make the exposition simpler. But these can be handled. And then we have Y, but now think of M as being humongous, very large, right? In the millions, tens of millions. So again, one of the characteristics of the problem is that most of the values are missing. Typically, it is a PU learning problem, but we have correlations between the outputs or labels. So personally, with my research group, I've done quite a lot of work over here. This is the first method, LEML, which I described earlier. Then methods that look for sparsity in the both the primal and the dual in the appropriate hinge loss kind of formulation of the problem. And then this area has been an active area of research for the past, I want to say a decade or so. So let's do a little thought experiment to just see the challenge of solving these prediction problems. So I've carried out this Wikipedia dataset example through the talk. So let's consider this Wikipedia dataset with 500,000 labels. Okay? So that's the output size. And let's think about there being 1.5 million Wikipedia articles. And I said that L is the number of labels or the output space size, and that's 500,000. The average document length is around 1,000 tokens. And so if we have a TF-IDF vectorizer, the vocabulary size is about 2.5 million. Of course, it is, each input is represented, or each Wikipedia article is represented as a sparse TF-IDF vector. So now suppose we take a very naive approach and we want to try and solve it as L, or 500,000 binary one versus rest classifiers. In this case, each classifier requires about 50 seconds to train, let's suppose by hinge loss, square hinge loss, or logistic regression. So if we then look at all this, the overall training time would actually be a lot, nearly 2 months if we use a 16-way parallelization, assuming full parallelization. And the memory requirement, since we need all these coefficient vectors for each of the one versus rest classifiers, the full model would require about 5 terabytes of disk usage. And things don't get any better when you start using neural networks. The memory footprint is still very high. For example, if you have a softmax, and the overall training time would be very bad. So the conclusion is that these naive approaches are just prohibitively expensive. So you can use some of the low rank techniques that I talked about before. Yes, that is a possibility. But then the inference time still is linear in the number of labels. So the challenges are that you have, possibly, let's say, greater than 10 million outputs. And many of the modern applications, suppose you are trying to do real-time inference, might actually require you to have inference latency, which is not in the seconds, but in the milliseconds, for example, 100 milliseconds. Like I said, there are a lot of missing values, and typically what you get in these examples is this long tail, which means that you have some outputs for which there are just very few observations, and there is a paucity or lack of training data over here. And then, as mentioned before, typically you only have positive training examples. And one of the keys to this method, to a better method, would be to try and identify strong negatives appropriately. So that's what PECOS does. It takes the, it basically has computationally efficient schemes for training and inference, which I will get to. It exploits correlation between the outputs, and this way you essentially can transfer training data from head outputs to tail outputs, or head labels to tail labels. And then, as I mentioned, it actually infers efficiently strong negatives so that the training for the rankers that I'll come to soon is actually quite efficient. So let's go into detail into PECOS. So in PECOS, we want to do the following. We have a very, very large output space, and we want to very quickly go, given a particular input, we want to very quickly identify a very small set of relevant labels. And then we can do something which is more expensive. So we were inspired by the field of information retrieval. And if you think of information retrieval where you have queries and you have documents, the number of documents are very large, and you want to try and retrieve documents that are relevant to a particular query, you can actually think of it as a very special extreme multi-label ranking problem, okay? And it has a very specific solution to this extreme multi-label ranking problem, which is you do lexical indexing, for example, using inverted index. You look at overlaps of tokens, so you have lexical matching. And then finally, you can use a learning to rank method to do a machine learned ranking method. So in general, for an extreme multi-label ranking problem, we have a challenge in the sense that each output might not have associated text. The inputs and outputs may actually not be in the same domain. And generally, the input instance is represented as a feature vector. But despite these differences from an information retrieval problem, we are actually motivated by these modern IR systems, and PECOS has a 3-stage framework. In the first stage, it does semantic label indexing. And the second step, you do matching, but in a machine learned manner. And then finally, you can do a machine learned ranking method, except that you have the ability to take ensembles of different methods. So let's go into detail into each of these stages. So in the indexing phase, what we want to do is we want to try and index all outputs semantically. Okay? And in the matching phase, once we are doing inference, what we want to do is we want to try and find the relevant indices or relevant outputs or candidate outputs very quickly using a matching technique. And then finally, we can use a ranking technique. Sorry, I think my screen, let me just do this again, view or control it. Okay. Sorry, so the correlated so the inference time then will reduce from being linear in the number of outputs to essentially being linear in the number of indices. And one of the techniques that we use is to do a hierarchical clustering of the outputs. And then it'll become linear in the number of clusters rather than linear in the number of outputs. Okay? And then finally, we need to do a ranking. So we are able to drastically reduce the complexity reduction. And by using a particular technique, we can actually get down the inference time down to logarithmic in the number of labels. So semantic indexing, we can use, I've already mentioned it, we can either use hierarchical k-means clustering. I'll show you some results. Those are based on this hierarchical k-means clustering. Or we can actually use some other indexing data structures such as an approximate k-nearest neighbor graph. And then ranking, we can either use TF-IDF features, or we can actually use deep learned features in the case when the inputs and or outputs have text features associated with them. Now, I want to spend a little bit more time on the ranking method. The ranking method, sorry, not ranking, but the matching part. The matching part is very critical because the matching gives you candidates, right? So we don't want to try and miss out on too many candidates. But at the same time, we want to prune down the search space aggressively. So when we do clustering, then the problem of finding the relevant clusters given an input, you can actually think of it as an extreme multi-label ranking problem itself. So that's what I've shown in this kind of toy figure at the bottom, right? So it's again an extreme multi-label problem. And now you can use methods, various methods. So you can use linear method, you can use other methods that have already been developed for this problem, right? But then if you are doing a hierarchical clustering, you can actually do this method recursively. So the matching can actually be done recursively. So you have, with hierarchical clustering, you have a tree that captures the clustering of the outputs into different clusters. And similarly, you can actually do matching by traversing this tree. So we call this method recursive linear matching. Now, in the case when I gave you the example of Wikipedia, and now in the case of Wikipedia, the input is in the form of text. So you can actually apply deep learning methods. So you can try different vectorizers, something which is TF-IDF, like I talked before, or you can try using deep pre-trained transformers, for example, BERT. But you can do one step better. What you can try and do is you can incorporate a trainable deep text vectorizer to get a deep learned matcher. Okay, so that's what we've done in one instantiation of PECOS. Now there are various choices for these deep text vectorizers. We could use BERT, or you can use XLNet or Roberta. And then when we do this training, C transpose yi just captures that you have to do matching against the clusters, not for the individual labels. And then you can have this trainable coefficient matrix W, which is again D by K. D is the output dimensionality of bird, and K is the number of clusters for which you are doing matching. And so what the idea is that you can actually learn W for this extreme multi-label ranking problem. So let me talk a little bit about results for PECOS. So Amazon Cat, it's not a huge data set. It has 13,000 labels, over 1 million training examples. And we call our method, so this previous method is called Xtransformer, and then the recursive linear method is called XR linear. So you can see here I've listed precision at 1, 3, 5, and then recall at 1, 3, 5. And in the red, I've denoted the best performing method. And I've compared it to, so Xtransformer gives the best performance in terms of precision and recall. XR linear is, it's okay. It's just a little bit worse. And then we've compared against these fast text algorithms that are also available. And then Wiki 500K is a much bigger data set. The number of labels is about 500,000, like I said. Number of training examples is nearly 1.8 million. And you can see over here that XR transformer actually outperforms XR linear by quite a bit. Okay, and fast text, I only have one number over here because it is the actual full softmax you cannot run on this size of problem, and the hierarchical softmax actually does not perform very well. So one thing I should note is that XR linear, one instantiation of, within XR linear, there are various choices for the representation, for how we do the indexing, and finally what we do for matching. And one instantiation of that is actually the Parabel algorithm by Manik Verma and colleagues. And so XR linear's performance out here is very similar to Parabel's performance. Now, Xtransformer or the deep learning method is the best performing method, but one thing that I don't see discussed that often is this performance cost trade-off. So I just want to highlight it. So how much actually does it cost to do training, and how do we compare these two different PECOS methods? One is XR linear and the other is Xtransformer. So what we did over here, now XR linear, we can actually train it on a CPU machine. So we have times over here given on an AWS machine with 16 CPU cores. And for Xtransformer, we have a P3 machine with 8 GPUs. And a P3 machine does cost quite a bit more, $24 per hour, as opposed to $1.25 for this CPU machine. So even though the precision of the XR linear is slightly worse on this data set, if you now start looking at the cost associated with training. So now if you think, well, you don't just train, this is the time to train just once, but if you're running a real application and it's deployed, then you may want to do either daily training or weekly training or monthly training. So if you see daily training, you're actually spending much more. And on this bigger data set, we can see that there is a substantial difference in performance. Precision difference is about additive 13%. But the daily training, if we try and do training daily, the Xtransformer actually costs over $3 million compared to XR linear, which is just $5 million. So that's one of the things that I want to try and emphasize, is that when it comes down to a practitioner, you really need to try and analyze the cost-benefit trade-off between the different methods. And one thing that is good about PECOS is it actually allows you to plug and play different methods for indexing, different methods for matching, and different methods for ranking. So it's time to conclude my talk. I've talked about these challenges of modern prediction problems, which have very large output spaces, millions, missing values, features with outputs, positive unlabeled learning, and then presented some solutions, including the PECOS framework for scaling up. And it's actually a very versatile framework, like I said, and you can plug in different methods for indexing, matching, and ranking. And there's still a lot to be done. I gave you the cost for neural network training, but that is really a cost in time, right? So if there is better, more efficient hardware that you can use. You can try and do more efficient neural network training and inference. One question is, in the PECOS method, even though we have like something which is indexing in build, can we do end-to-end training? And then instead of just ranking, if we are trying to use it and deploy it in a real system, can we actually have extensions to contextual bandits and to reinforcement learning? So that concludes my talk, but I definitely want to thank my collaborators. These are former students, many of whom are colleagues now, and I'm very grateful to all of them for the hard work they've put in over time. And if you're interested in some of the papers that I've mentioned during the talk, here is a bibliography. Okay, well, I thank you very much for listening. Let's see how our eager audience is doing now. Uh-oh.